In 1987, IBM released the Personal System 2 and brought many new inventions that would live on, in some cases for decades. One of the PS2 inventions was the microchannel architecture. MCA was technically superior to ISA and allowed for higher speed communications within the system. Transfer speeds were on par with a much later PCI standard. Only problem was, the clones couldn't clone it. So unlike the other inventions that became standard, the MCA bus never took on. Another great product released the same year was the AdLib sound card, the first de facto standard sound card for PCs. There were AdLib cards made for the MCA bus, but they are silly rare, because the standard never took off. Luckily, TubeTime reverse engineered the card a few years ago. So today we're going to build an AdLib replica for the MCA bus and try it out on an IBM PS2 Model 50. To build one of these, I got some PCBs from the sponsor of this video, PCBWay. If you're playing along, you can go to TubeTime's GitHub page and download the Gerber files. And then head over to PCBWay.com, click PCB Instant Quotes, and then quick order PCB. And here you can add the Gerber files. And that's pretty much all you need to do to order these PCBs. You can also find the bill of material on the same GitHub page. Okay, let's start with the trickiest part first. And that is the CPLD. And apparently I ordered the components back in July. So I'm a bit behind. Bake part if 60% is not blue. Well, I don't have the faintest idea if this is a level 2 project or level 2A to 5A. So I'm just gonna ignore this. So this is actually the second revision of these boards. The original replica had an 82C611, just like the original card. And those cards actually don't work with some faster systems. So the original replica will work with the Model 50, and I suppose the Model 62, but it won't work with the Model 70 and faster. So he redesigned the card to use a CPLD, and this version should work with faster systems too. Okay, let's start by adding some flux. The important thing here is to align the notch, of course. So, aligning a chip like this with the camera on top is pretty much impossible. So I'll take this off camera and solder two of the corners. Okay, a couple of the pads are soldered. So let's add some flux. I haven't soldered a chip with tiny legs like this in ages. So next I'm going to drag solder and ignore the bridges for now. There are other methods to soldering chips like this. But this is quick and easy. Now we can drag solder the two sides that already has a couple of legs soldered. The key to making this quick and easy is really good flux. And not applying too much force, because that will bend the pins. Okay, next we need to remove the bridges. Not sure how well this will show up on camera. But when you drag solder like this, you pretty much always get some bridges. I find the easiest way to remove bridges is to just drag solder the same row of pins a few times and remove the solder I have on my tip. And after a couple of times, all bridges are gone. Soldering a chip like this may look a bit scary first time, but it's definitely not difficult. Okay, the next step is to dip a Q-tip in IPA and clean up the flux. I usually don't use a brush, because then you have to clean the stupid brush. Okay, before I clean some more, I'm gonna grab my loop and do an inspection. Okay, board cleaned up, and I did an inspection. And I'd say this is good enough for me. For some reason, I managed to order these absolutely tiny resistors. But hopefully I have enough normal resistors in my stash. Okay, first out is R3. That's a 2.2K resistor. Oh, I should have ordered some larger resistors, but at least these look better than the tiny ones I ordered. Same thing goes for R4 here. R7, R8, 12, and 13. Next we have one 12K resistor at R5. Next we have a couple of 10K resistors at R6, R10, 11, and 19. I love the artwork on this PCB, by the way. It's been very playful. Next we have one single 1.5K at R9 here, 8.2K at R14 here. And finally we have three 10 ohm resistors at R16, 17 up here in the corner, and the last resistor is R18 up here. I guess we better solder before it gets too messy. I haven't done any projects like this in a while. I have to say, I rather enjoy it. It's very rewarding to build things up. I have never programmed a CPLD before, so that is going to be interesting. Always fun to learn something new, if I can figure it out. So the cool thing about learning electronics nowadays is that it's always a helping hand online. Compared to when I was a kid, if you got stuck, you get stuck for a very long time. It could take months before you found the information. But nowadays you can just Google when you get stuck. And when you don't find the information, there's always someone willing to help out. And then there are videos like this one, of course. Although I don't think there is a video for this project yet. Well, I guess there is one now, if you're watching this. Okay, all the resistors are in, and I didn't have to use any of those tiny resistors I ordered by mistake. Next up we have the only diode on this board. CR1 here. And it's a 1N914. So next I'm gonna go with the sockets. So we've got one large 24-pin socket here for the OPL chip, and one tiny 8-pin socket for the most expensive part, according to the silk screen. One 14-pin socket here for an op-amp. Another 8-pin socket here for distortion generator. And then we have a 20-pin socket for data lurch. I'm sure that wasn't the original silk screen that Adlib used. And finally one 14-pin socket for shifty levels. I tend to solder just one pin on each side in the middle. And before I solder the rest of the pins, I make sure that the socket sits flush. It doesn't really have to work, but it looks a bit dodgy if the sockets aren't straight on the PCB. So now I can remove the sticky tape and check those sockets. Okay, all sockets are flush. And we can go ahead and solder the remaining pins. Yeah, when I was a kid, I had to make my own PCBs. Literally. I had to buy large sheets of plain PCBs and then cut them to size. And I used a special pen. I think it was leaded ink. And then I had to dip those damn PCBs in a nasty acid to etch away the remaining copper. And you can be sure they didn't look too good. Nowadays we can order fancy PCBs like this in less than 5 minutes. Things have really changed for electronics hobbyists. By the way, if you're not into soldering, there are pre-built cards on eBay. And this project has been around for quite a while now. So there are some modern versions of it too, with surface mount components. But this is the fun way to do it. Okay, that was the last socket. Okay, next we have the two transistors. So I'm gonna bend the legs a bit to make them fit. So first we have Q1 here, and that's a 2N3904. Oh, I was mistaken. There's only one transistor on this board. And this is a 7805, a 5-volt voltage regulator. And it's U11 up here. Okay, this is moving along quite quickly. Time to put some caps in. And some of these are tantalums. And they are labeled Snap, Crackle and Pop. So I think I'm gonna skip ahead a bit here and install all the caps. The important thing with tantalums is to make sure that the polarity is correct. Otherwise they are indeed going to snap, crackle and pop. That was quite a lot of caps actually, so that took a while. So I skipped ahead here a bit. The board is very clearly marked, so you don't really need an instruction. Aside from programming that chip, of course. Next up we have the only electrolytic cap here. Like so. The only remaining part to solder now is the volume knob and the audio jack. Okay, I did an inspection and I only made one mistake. Bonus points if you noticed. To program that chip we actually need to solder one more thing, because we need to attach these wires. So we need to solder in a row of pin headers. And just like the rest of the board, these are clearly marked too. This is where I normally would wash the board, but to get the video out on time I'm gonna have to wash it later. So let's get some chips in those sockets. U1 here is a 74LS245. Next up we have a 74 ALS04. I'm not sure if it has to be an ALS series. I just ordered the available bill of material. Oh, I completely missed that this board has one surface mount component. Good thing I didn't wash the board. This would have been slightly easier to solder before I install those caps. But not a big problem. But if you're playing along, you may want to solder this component in the beginning when you solder that chip. Next up is an op-amp. This is an RC4136 at U9. Our next chip, and the last chip that is actually still made, is an LM386 power amplifier at U10. All the components we have used so far are available to buy brand new, but there are 3 components that are not. So you're gonna have to source these on eBay or AliExpress. So firstly we have the Yamaha OPL2 chip, the YM3812, and then we also have the DAC, and it's a Yamaha YM3014B. And the third part we are gonna talk about in a second. So let's install these first. And they are of course U8 and U7. The third and final part that isn't main anymore is the bracket. The best solution is to print one, of course, but I don't have such fancy equipment. So I'm going to borrow a bracket from an external floppy controller that I'm not using right now. This is far from ideal, and it obviously has a large gaping hole instead of one hole for the audio jack and one for the volume knob. But this should work. That was quite tricky to assemble, so I had to do it off camera. It's ugly, but it works. So this will have to do for now. Okay, time to program that chip. But first, I double-checked all the components on the board. And if you were paying attention, you may have noticed that some 3.3K resistors had found their way into my bag of 10K resistors. So that has been fixed now. To program the chip, I'm going to use DLC9LP clone. Connecting it is very simple, because the included cable is clearly marked. And same thing with the board. So that was super simple. I had to add a second pin header on this side of the board, because we are going to need 3.3 volt external power. Like so. And I'm going to use my bench power supply. The next thing you need to do is to download the bitstream from the GitHub page here. Create a folder on your desktop. You can call it what you want, but VMshare is a good name. Place the bitstream file inside that folder. And next you need to download Oracle's VirtualBox. I went with the Windows host here. During the installation you will be prompted for a shared folder. When you do, just point to the folder that we made on the desktop. Next you need to Google for Xilinx ISE 14.7, and I went with this Windows 10 version here. When the installation is done, double click the impact icon, and that should bring you to this desktop here. I was expecting it to start impact right away, but apparently it didn't, so double click impact again, inside the desktop. Hopefully you will get this question here, and you should click yes. And then OK. And now we're getting an error, because the programmer can sense that the board isn't powered. So now you need to turn your bench power supply on. And the LED should now turn green. So if we start the software with power connected to the chip, and again, when we're prompted to automatically create and save projects, and we click yes and OK, you will be prompted for that JAD file. So if we click yes, and in here we can access that folder that we have made on the desktop. And here's our bitstream. So I'm going to click OK. If it's a used chip, then you should erase it first. And blank check. Part is blank, so we're ready to program. Right click on the chip and click program. Installing the software will probably take you about an hour, but the remaining programming process is going to take you less than 5 minutes. So if you're anything like me, you're going to right click and verify, and you're done. That chip is now programmed, and at least in theory, we should now have a working sound card. So I'll disconnect the programmer, and we're ready for a test. Before we test the card, there is something else we need to fix. The fan in my PS2 is incredibly noisy. In fact, it's probably louder than the AdLib card. So I have removed the fan from the fan assembly. And I bought myself a Noctua Redux NFR8. And this fan is the same size as the original fan. But this fan should be very silent. So first I'm going to chop that cable off and remove that sleeve. We won't need that yellow wire, so I'll just chop it off. Before we install the new fan, we need to check the direction of the airflow of the original fan. And it's clearly marked with these arrows. And the Noctua fan is clearly marked too. The wires are fed through this hole here. The wires are then soldered to the PCB. The polarity is clearly marked on the PCB. Then we can just snap that PCB in place on these two tabs. This IBM should now be nice and quiet, so we can enjoy some AdLib sounds. Now we can install that sound card in one of those weird and wonderful MCA slots. The fan assembly is toolless, so it just snaps in place, locked with these plastic tabs. We'll tackle that noisy Apple drive in another video, but it definitely needs to be replaced with something more suitable. There is actually one more minor thing I want to try out today. So these IBM PS2s use these rather awkward batteries. So I grabbed some female pin headers and cut one piece to size. And then I grabbed a battery holder for two CR2032s. They are connected in series, so we're getting about 6 volts. And if we connect it to this connector down here, we should now have 6 volts here. We do, 6.6. Then I guess we need to store it away here somewhere. Oh, there's actually a perfect slot for it here. Yeah, I think that's a better solution than these bulky old batteries. Let's give this a try. Well, let's be bold and put the lid back on before we do the tests. Okay, let's see if that sound card works. Okay, got a pretty loud pop in my speakers, so that's a good sign. We are going to have to install the sound card, and we're also going to need to reinstall the SCSI controller since we popped that battery out. If you're not familiar with IBM PS2s, to access the BIOS you need a reference diskette. These are easily found online. And a reference disk basically boots you into BIOS. And this is also where you install the drivers. So we're gonna go down to set configuration. The description file for the adapter in slot 1 was not found. In slot 1 we have the AdLib card. So I downloaded the ADF file from the GitHub page. So let's install it. Now we're getting the second warning. The description file for the adapter in slot 3 was not found. That is my SCSI controller, and it's a future domain MCS 350. So I'm going to insert the diskette with the ADF file for the controller. Now we are prompted for the reference disk again. The fixed disk type could not be read from the fixed disk. I think that's perfectly normal. It just means that the IBM couldn't recognize my Apple drive. I can't blame it. And now we can go back one step and set features, date and time. And I'm actually right on schedule, so I can upload on time. Okay, I think we're done in here. Now let's reboot and see if it boots to the hard drive and recognizes our AdLib card. And it boots without errors. So let's test that AdLib card and see if it actually works. Okay, fingers crossed. Yes! Oh, that was a bit loud. It works! Awesome! Let me move that audio cable and record this sound. Okay, I moved the cable. So what you're going to hear now is a recording directly from the AdLib. And it sounds awesome! So finally I got some AdLib sound in an IBM PS2. What a great project! I'm not gonna call it cheap, because it's not. But the cost is a fraction of what a real AdLib card would cost. And even if you have the money, you still need to find one. And that's almost impossible. So, how about some Monkey Island tunes? By the way, I just opened up my mail, and I think I have all the parts to repair and overclock the PC Junior some more. I'll have to double check, but we are probably going to repair and overclock the PC Junior next week. And now is a good time to watch the video where we build a custom adlib for regular ISA slots. I'd like to end this video by saying thank you to my patrons. Thank you for your support. If you want to become a supporter of this channel too, consider becoming a patron. You can use the link in the description. As a patron, you will have early access whenever possible. Thank you for watching. You can also support me with a like and a comment. If you're a regular viewer, consider subscribing to this channel.